Okay, continuing on with our review, we'll look at Module 4, where we talked about analyzing graphs and also piecewise defined functions. And so you see here in problem 1, we've got a function defined by two different pieces. This is a piecewise defined function. We have a linear part. We have negative x minus 2 for all x values less than or equal to negative 1. And we have a quadratic function, f of x equal to x squared minus 4, for all x values greater than negative 1 and less than or equal to 3. So it wants us to graph this function. So what I want to do is look at the two pieces, and let's get a table of points for both pieces. All right, so let's go ahead and talk about f of x equal to negative x minus 2. All right. And the key thing is the restriction. X must be less than or equal to negative 1. So what we're going to do, all right, let's go ahead and build a table of points based off these restrictions. So let's find some x and y values, right? So with that said, always start with the restriction. So we have x less than or equal to negative 1. Well, let's begin with negative 1 and see what we have. Now, with that said, since it can equal negative 1, this point that we plot does need to be a closed circle. It needs to be part of the graph because of the equality. It can equal this, less than or equal to. All right, but always start with the restricted values. Make sure you include those. Now, what's the y coordinate? So we're going to have to evaluate the function at an input of f of negative 1. So that gives us, what, negative 1 minus 2. And as we simplify that, we get what? Negative 1 is 1. 1 minus 2 is negative 1. So as the ordered pair goes, we have a point to plot. Right? We got negative 1 to go plot. So as we begin graphing this piece, we can go over here to the side and plot that point. Right? We know this point's going to be on the graph. Right? This is the ordered pair here of negative 1, negative 1. And let's go ahead and find a couple other points. So what's another value we could use? So again, based off our restriction, x must be less than or equal to negative 1. So we could use negative 2. I just want some quick, easy integer values to work with, right? Nothing complex to plug in, but I could plug in negative 1.1 if I wanted. Any number less than negative 1. So I'm going to plug in negative 2. So that's a value less than negative 1. So as we do the evaluation, what's f of negative 2? What's negative of negative 2 minus 2? And, of course, negative 2 is 2. 2 minus 2 is 0. So we can go plot the ordered pair, negative 2, 0. So we know this graph of this is a linear function, this piece, negative x minus 2. We know it passes through the point negative 2, 0. So there's another ordered pair, right, on this graph. And maybe just to get a little more detail, let's do one more. What happens at negative 3? Well, f of negative 3, that's equal to negative of negative 3 minus 2. And that's 3 minus 2, which is 1. So we're going to pass through the point negative 3, 1. So left 3, up 1. So there's that ordered pair, negative 3, 1. Now, this line, of course, goes on forever, right? So as we're looking at this piece here, let's go ahead and graph it. So it passes through these points. So there's a sketch, right, of that piece of the function. Now, that takes care of the first piece. Now, I want to look at our second piece. So let's go ahead and talk about the next piece, which is f of x equal to x squared minus 4 for all x values that are greater than negative 1 and less than or equal to 3. So restricted between negative 1 and 3 as far as inputs go. So let's build a table, write a table of points. So if you want, we can talk about these x and y values. So I'm going to start with the restriction, -1. So I'll plug in -1. Now this will be on our graph. I'll make a little note, an open circle. This point we will not include because we got to be greater than -1, not greater than equal to. Greater than equal to, we would include it, right? Less than equal to, greater than equal to, closed circle. Less than or greater than would be open circle. Now as we evaluate, of course, that's f of 0. I'm sorry, not f of 0. F of -1. And f of -1 is equal to -1 squared minus 4, which is 1 minus 4, or -3. So we know this was going to pass through the point, what? -1, -3. So we could plot that point. So over here, we got -1, left 1, down 3, -1, -3 right here. A little open circle. So again, that point, that ordered pair, is not part of the graph. It's where this graph takes place to the right of that point, right? All the x values greater than -1. So let's do another ordered pair. So let's do 0, right? 0 would be an easy value, another integer value that's greater than -1. So what's f of 0, which anytime you let x be 0, you're going to be finding the y-intercept point. So let's see what this ends up being. This is 0 squared minus 4, x squared minus 4. And that's 0 minus 4, which is -4. So this passes through the point 0, -4. So 0, -4 is a point on this graph. Right? And let's do some more, a couple others at least. Let's go to 1. What happens at 1? That's another value we could use. So you see it's quadratic. We're getting a curved piece. We know quadratics. We've seen our parabolas. They're U-shaped or upside down U-shaped, depending on if it's x squared or negative x squared. And since this was a positive x squared, we're going to have sort of a U-shape going to it, but there's a piece of it. So it's a piecewise function. What's f of 1? F of 1 is equal to 1 squared minus 1, which is 1 minus 4, or -3. So it passed through the point 1, -3. So we can plot that point. So 1, -3 is on this graph. All right. And maybe one more. Let's go to 2. Let's find one more point. A little more detail. What's f of 2? That'd be 2 squared minus 4. 2 squared is 4. 4 minus 4 is 0. So here's our actually finding our x-intercept point, right? 2, 0. So this graph passed through 2, 0 also. Now at that point, we got enough, right, to give a accurate graph. So let's go ahead and connect them. All right, and there it is. There's the second piece. So you can see that piecewise defined function. Right, we've sketched it using some integer values, some easy points to go plot. All right, now let's analyze this piecewise defined function. So state the domain of the function in interval notation. So remember, domain, right? Domain are all your x values, right? All the real number values of x that make up this function graph. So ask yourself the question, where do you see this graph take place on the x-axis? Well, it covers the entire x-axis, right? This left piece goes to -infinity, right? It keeps a line right here going on forever, that piece, part of a linear function. With that said, we do know at -1 on the x-axis there was a break in the graph, right? But that graph continued at -1 with the next piece to the right. So -1 is in the domain. So as we write our domain, of course, the second piece goes on forever to the right. So this graph covers the entire x-axis. This is a domain of all real numbers. So our domain, as I like to write it in interval notation, all real numbers x, -infinity to infinity. Now range are the y values, right? Range is where the graph takes place on the y-axis. So we want to ask ourselves that question. Right? Where is the y values? Now I always like to look from bottom up. I always look at the smallest range value. What's the smallest y value? So domain are all the x coordinates from all these points in the graph. The range is all the y coordinates, all the y values. And you can see this graph, right, it goes down to what? -4, that y-intercept point. That's the lowest point on this graph. And then it goes up forever, right? Even though there's a break, right? This blue curved in piece, this quadratic piece, goes up forever. So it covers from -4 all the way to infinity. So our range, right? So we're writing out the range right here in blue. Range is where our graph takes place on the y-axis. And it's all y values greater than or equal to -4, right? Begins at -4 and goes up forever, right? On that quadratic piece there. And that defines the range of this piecewise defined function, that one piece there. Now, how about the next question? Let's find the y-intercept. We always want to know where our intercepts are. If we have a good graph, we have all the intercepts labeled. And we know the y-intercept point, right? We've got there from that second piece, 0, -4. Now, the x-intercepts, we also have those labeled. There's 2 of them, right? The x-intercepts, we've got 2 of them. So one of them is at -2 on the x-axis. So -2, 0. And then we've also got one at what? Over at +2, 2, 0. They're the x-intercepts. So at -2 or 2 are our zeros. Is the function continuous? All right? Is this function continuous? All right? No. What do we mean by continuous? So as we're looking through the domain of this graph, if we take our pencil and we were to trace this graph, right, we'd have to pick up the pencil. There's a break in it, right? It's not continuous. It's continuous if you ever have to pick your pencil up through the domain. So it goes on forever, right? You don't ever have to stop with your pencil as you're going from left to right along this graph. So yes, this is a continuous function, right? I'm sorry, no. I mean, not no. We do have to pick it up. So this one definitely not continuous, right? We got that break in it. So if we didn't have that break, yeah, it would be a continuous function. But we have that break from -1, -1 on the first piece to what? -1, -3 on the second piece. So it's not a continuous function. All right? So again, that's a piecewise defined function. All right, let's move on to, let's do one more example. Move on to our next problem here. As we look at our next piecewise defined function, we got another one similar. We got a quadratic piece to it, and we've got a linear piece. So I want to do the same thing. I want to build a table of points and sketch it so we can analyze it. So let's go ahead and do that. And I'm going to go ahead and talk about the first piece. So f of x equal to -x plus 3 squared. And here's the important part, right? Remember, right, we're looking at all the x values that are greater than -5 and less than or equal to -1. So those are our restrictions. Those are important. We need to make sure we include those, right, when we build our table of ordered pairs. So let's go ahead and do that. So we got our x and y. Let's build a table, get some quick points to go plot. So I'm going to start with -5, right? It has to be greater than -5. And you won't put a little open circle there, as we know -5 will not be part of the graph because, again, it's greater than, not greater than or equal to. What's the y coordinates? Let's go evaluate our function. So f of -5 equal to -5, right, plus 3 squared, which is equal to negative of -2 squared, right, as we simplify down. And of course, -2 squared is 4, so I end up with -4. So my point on the graph of f of x, this piece, this quadratic piece, will be -5, -4. So at -5, -4, let's go ahead and begin to look at this graph. Right here is -5, -4. You see I'm putting in that open circle, right? Not part of the graph. That's important. All right, let's go ahead and do some other points. Let's do -4. what's f of negative 4 going to give us? Now again, negative 4 is something we can use. It's greater than negative 5, is less than, equal to negative 1. As we simplify, we got negative 4 plus 3 squared. So we take the negative of that. Well, negative 4 plus 3 is negative 1. Negative 1 squared is 1. So we end up with negative 1. So we get the point negative 4, negative 1 to go plot. So we're going to pass through the point negative 4, negative 1 right here. So I'll go ahead and label that ordered pair. And then we could find some more. Let's go ahead and do negative 3. F of negatives to the integer values. Get a detailed graph against a curved piece. Right, it's part of a quadratic. All right, and this one's going to be a little upside down U shape going on with it, because we have a negative x squared term. But as we simplify here with negative 3 plugged in, all right, what do we get? I get the negative, well, negative 3 plus 3 is 0. So we get negative 0, which is 0. There's no negative value of 0. So we have negative 3, 0. So we found a x-intercept point, which is always important. And we'll go ahead and plot that point. And as far as integers goes, there's only 2 more to find. So maybe we'll go ahead and finish off the integers. How about f of negative 2? Well, that would be the negative of negative 2 plus 3 squared, right, which is the negative of 1 squared. And negative 1 squared is negative 1. So negative 2, negative 1 is a point this graph, or this piece goes through. So I'll go ahead and label that point, negative 2, negative 1. And then our last value, we got to always use the restrictions. Remember, it has to be less than or equal to. And I'm going to put a little closed circle beside this. So let's go find f of negative 1, which is equal to negative of negative 1 plus 3 squared. So I got the negative of 2 squared, which is negative 4. So I have the ordered pair of negative 1, negative 4. So negative 1, negative 4, I'm going to put in a closed circle, and that's the end. Let's go ahead and connect these. So what does this piece look like? So there's a sketch, that quadratic piece. All right, so now let's go build the second piece here. So now we're looking at our second piece from our function. So we got f of x equal to 2x minus 2 for all x values greater than negative 1. So as we build our table of ordered pairs, our x and y points, now greater than, a little open circle here, right? Because we're not going to include this point, all right, from this piece. Now with that said, what is the y value? What's the y coordinate? So what's f of negative 1? That'd be 2 times negative 1 minus 2, which is negative 2 minus 2, which is negative 4. So we get that point again of negative 1, negative 4 we found in our last piece. So open circle, well, we already have that point included from the other one. So we do include negative 1, negative 4, but it's not defined from that linear piece. It's defined from the quadratic piece. Now we need a few more points, at least a couple. This is a line. It won't take long to find out what the graph's going to look like. 2 points will give us an accurate picture of the slope of the line. But with that said, let's do another one. Let's let x be 0, right? That's the integer value greater than negative 1. And that's going to let us find the y-intercept point. And we let x be 0. So I've got 2 times 0, right, minus 2, which is 0 minus 2, or negative 2. So our y-intercept point in the second piece is right here at 0, negative 2. So this line passes through 0, negative 2. All right, let's look at 1. Do another one. What's f of 1 give us? That would be 2 times 1 minus 2, which is 2 minus 2, or 0. So now we're finding the x-intercept point. 1, 0, this line passes through. And that's enough. I do have all my intercepts. I'm going to go ahead and graph in that second piece. But there it is. There's our piecewise defined function. Not hard, right? We're just finding some easy points to plot based off the restrictions. State the domain. Just analyze it. So domain, let's find all the x values that make up the graph of this function in front of us. Where does this graph cover the x-axis? Well, our minimum x value, how far to the left does this graph go? We're going to left and right for domain, right? On the x-axis. It begins at the point negative 5, negative 4, except that's an open circle. So as I write my domain, I need a parentheses on the -5. All x values, what, greater than -5. From -5 on to infinity, you'll see your graph. No matter where you look to the right -5, you'll find your graph of this function from one of those two pieces. So all real numbers greater than -5. So we don't see anything to the left of -5, and we don't include -5. Don't put a bracket. Right? Bracket means we want it. -5 is undefined based off the restrictions from our first piece having to be greater than -5. Our range, where's the graph cover the y-axis? Let's list all those y values. Well, how far down does the graph go? Well, you can see our graph right here at -4. -4 is the minimum y value. Now, -4 is included, even though -5 and -4 is not part of the graph. Right? We have our point over here at -1, -4. So we need a bracket on -4 all the way to infinity. So -4, all y values greater than or equal to -4. Find the y-intercept. The y-intercept point we've already got labeled from that second piece, 0, -2. Our y-intercept. And our x-intercept, we have two of them. We have one at -3 on the x-axis, so -3, 0. And we have one at x equal to 1. It's another 0, so 1, 0. Is this graph continuous? Yeah, if you take this graph on the domain, right? If you look x greater than -5, you never have to pick your pencil up. This one is continuous. No breaks to write a -5 where our domain take place. So that's piecewise defined functions. So that's the first thing we did there at the beginning of Module 4. So it's a good review of piecewise defined functions. Back from Module 4, it's the lecture. So we'll take a break and continue on.